and assistant in neuroscience. His research focuses again on development of algorithms for interpreting and analyzing biomedical images. And we will talk tonight about live image-based neurosurgical guidance and the roadmap generation. So I invite Victor to share his screen with us. Please, Victor.
Yes. So now can you see my presentation and can you hear me fine?
Yes, perfect. Go ahead.
Well, thank you, Enrico, for the introduction, and it's really a great pleasure, this opportunity to present some of our work that we've been doing in Zurich on the title is Novel Applications of Machine Learning for Operative Visualization. I will focus on that, but I will give kind of a tour de force through different kinds of applications of machine learning in neurosurgery and what we think might be the clinically most useful ones. My disclosures are not relevant to today. And I want to start off with this level of evidence pyramid that I adapted from these usual level of evidence pyramids to try and classify kind of machine learning studies in clinical medicine. So some important points that I would like to talk about is, first of all, that really most, maybe 90% of the studies that are being published right now on machine learning in medicine, whether that's neurosurgery or other fields, are in this lowest tier 3 level. So these can be studies publishing high quality data for model training, a lot of pilot studies, feasibility studies, looking at new kind of ideas that we can tackle with machine learning, comparing the performance of algorithms against human experts, looking at new methodologies and updating and improving already existing algorithms. And then once you have really good amounts and good quality data and proven methods, you can get into the second tier, which is basically algorithms that work well in silico. So we know that they work, we know that they're robust, and for that we can do external validation studies, which is a really important step. We can try to maybe generalize our models more by using data from multiple centers and looking at the performance in multiple centers. And we can look at how to best deploy these models in clinical practice. But the main point is that this level 1 evidence, which for me is any demonstration of a clinical tangible benefit to patients through the use of any kind of machine learning algorithm, that's really not been reached almost at all. Certainly not in neurosurgery that I know of, and as far as I know, also not in other fields where we really have like a proven benefit, the reduction of complications or cost reductions like that. That is something that has been less focused on up to now, and that's really, I think, our thing that we have to focus on in the next 10 years to get to this next level. So not only show that the algorithms work on a computer, but that whether they actually help. And we think that we have an idea which kinds of applications will be more useful and which kinds of applications will in the end be less useful effectively to patients. So what I want to start off with is kind of the prototype of machine learning in medicine, which is clinical prediction modeling, because that's really the easiest to get started with. Nowadays, there's many packages, many easy ways to get started with, especially clinical prediction modeling. And what do we expect from clinical prediction modeling? So to answer these questions that we get by patients, like what is my risk, for example, for neurodeficits after brain tumor surgery, to answer these questions with some more objectivity. But this is something I saw abroad recently. After all, it's impossible to predict. There's also this famous quote by Niels Bohr, attributed to Niels Bohr: predictions are very difficult, especially if they concern the future, because well, we think that it's really very difficult to predict the future because there's so many factors, especially in neurosurgery, that contribute to how long-term outcomes really are. And if we want to build models that really do provide accurate predictions for that, then we have to build very complex models with a lot of inputs, which again, in medicine, we won't have the amounts of data for that we need. So we don't have millions of observations like Google has with cats and dogs classifiers where there's millions of images. We have thousands, in the best case, maybe tens of thousands of patients. So that's why probably this highest level of evidence, so clinical benefit, might not be reached for clinical prediction modeling in medicine. But still, I'm going to show you a typical example. of clinical prediction modeling in brain tumor surgery. So unfortunately, we are maybe not as good as we think as neurosurgeons at predicting the outcomes of neurological outcomes after tumor surgery, as this study showed. And how do we usually tackle risk stratification? We make classifications. We love classifications in medicine, right? So especially in neurosurgery, we publish a lot of classifications every day. One example might be trying to predict the chance of gross total resection in pituitary adenomas, where there's cross classification, maybe also the Zurich pituitary score. These scores, they are robust. We know that they work well, but in the end, they really only stratify patients into 3, 4, 5 different risk groups. So that's quite a crude classification. It's not that we can really talk about individualized risk, about precision medicine or personalized medicine yet. So this is where machine learning might, at least in silico, come in and be able to provide more accurate and more objective, kind of an objective second opinion of these surgical risks. And this is the study that we performed, which was, I guess, kind of an ENS study, because a lot of centers from all over Europe participated. And we see that we did achieve a generalizable model that was able to predict the risk of a new neural deficits after brain tumor surgery quite well, but the performance was not as such that we would expect it to lead to any changes in decision making, which in the end would lead to a clinical benefit. That has to be tested. Of course, you can make a nice web app, which we did. And that leads me into the next point, which might be a little bit more likely to be clinical useful, which is any kind of application of machine learning towards personalized medicine or precision medicine. So trying to look at patients really as individuals, whether that's a objective functional test in spine surgery, such as this one. So today I'm going to show an example of this 5 repetition C2STEM test, which is able to classify the functional impairment of patients with degenerative spinal disease. But you could also talk about blood tests, whether that's CRP or D-dimers, any test or anything that we measure basically where we know that not all patients are the same. So we know with D-dimers, for example, if we want to diagnose or exclude pulmonary embolism, older patients have very high levels of D-dimers. So you cannot use the same cutoff for every patient. The same here. In this table, you saw that we have this 10.4 second cutoff. So based on that, you would say any patient that is slower than 10 seconds is fine, and anyone that needs 10.5 seconds is not fine. But that's a very crude classification. You would like to take into account also the age and the gender and the smoking status, etc., all the demographics of the patient to see what, on an individual basis, they should be able to achieve. One way you could go is an unsupervised way that we also did, where we can kind of, using all the demographics and the test performance, try to identify groups that are somehow similar to each other, and that we, in this case, show to be predictive of severe depression and functional recovery. But what I've really been talking about is what we've integrated in the end in this app, which some people are starting to use right now for this C2STEM test, which if you look at the third screen, that screenshot, you can see that this app is able to, using machine learning, calculate for every single person what they should be able to do in terms of their C2STEM test performance. So for this patient, it says 10.3 seconds, but for an older patient, maybe who was a lifelong smoker, it will say you are fine if you take 16 seconds, and for a young rugby player, might be 8 seconds. So that's personalized medicine. Yes, so these two applications, clinical prediction modeling and personalized medicine, might show clinical benefit, but we don't really know. Now I'm going to focus on the main part of the talk, which is operative visualization, because we think in Zurich that that's really the most plausible point of attack for machine learning in neurosurgery, because we rely so much on imaging for surgery, for setting indications for surgery, and that's why I'm going to show you some examples of that. So the first, maybe most basic or most popular application of machine vision in medical imaging is probably segmentation. So semantic segmentation, trying to cut out specific structures. Why would that be useful? Well, we can have volumetric assessment, we can do that in a more automatized and quick way, and we can also generate 3D visualizations, as Enrico showed, for mixed reality applications, for example. So these are things that have been done often. For example, brain tumor segmentation is a very popular task. This is our algorithm, but there's many more. On the left, you see the performance on preoperative, so preoperative brain tumors, where it really works quite well. And then to the right, maybe this is more of a neurosurgical problem, and it's something that has not been done so often, is trying to segment the residuals after surgery. So that's, of course, much more difficult, and the performance was radically lower, because we know as neurosurgeons that also for the radiologist or for the neurosurgeon, it's not always clear whether something small is hemostatic material or a vein, or is it really a true tumor residual. So those things again limit maybe in the end the clinical benefit of these things, because it's just a very difficult task. Then this is spine segmentation, also something that has been done before. We just tried maybe a tiny little bit different approach, maybe a bit more neurosurgical approach, by first detecting the levels and cutting each single level out, because we really wanted to have a very, very accurate segmentation of the bony structures of the pedicles. So by cutting each vertebra out and segmenting each vertebra by itself, we are able to process these in their native resolution. And we found that we were able to have a very accurate segmentation of the vertebra in this method. And then you can do also other things, segmenting adenomas or ventricles. Ventricles might be useful because we do that a lot in clinical practice, right? We look at the changes over time in the ventricular volume. And this is a toolkit which we've developed, which you can use on your own PC and download from our website, which I will show again at the end. This toolkit, which allows you to do those things. Now getting maybe into some more novel applications. What we like to focus on is what we call synthetic imaging. So we think that probably the highest benefit of machine learning clinically will be in those applications where we are really trying to do things with machine that even human experts cannot do. So segmentation, we can also do it by hand, but it just takes a while. But trying to do things that seem impossible, like for example, there have been studies, some of them have been retracted now, getting the IDH mutation status from glioma MRIs, for example. That's a thing that we cannot really do as radiologists or as neurosurgeons, but it might be clinically useful. Talking about synthetic imaging, this is the first problem that we tackled together with MRI guidance from the Netherlands. In the case of trying to spare making a CT of the lumbar spine when we do navigated or robotic spinal fusion, for example. So how nice would it be if the patients, usually they come with a lumbar spine MRI, but don't necessarily already have a CT. In Europe, it might not be so difficult to make an additional CT, but that's not the same case everywhere. How nice would it be if we could just generate, for every patient that has a spine MRI, generate a quite good CT, and that way eliminate radiation, eliminate costs, eliminate unnecessary logistics. So the goal was to develop a generative algorithm that can create a high quality CT from an MRI. And these were the results. Actually trained with just a couple of patients. And to the left, you can see the comparison of the actual MRI and the actual CT, and in the middle, the synthetic CT. So it looks a little bit different, but it would certainly be good enough to also mathematically, it was not significantly different to the real CT. So you could actually plan your screws on that. You can also make 3D visualizations, of course. And on the right, we see kind of a real life application for patients where we didn't even have a real CT, only the MRI and the synthetic CT. So that worked quite well. And this is a small piece where we showed that you can also do the robotic planning on these synthetic CTs, that the workstation will accept these synthetic images, etc. A second thing that we're working on is another approach to synthetic imaging, where we're trying to generate CTs so tomographic imaging from X-rays or radiographs. So, I mean, for example, we will not expect, for example, for the skull CT to have perfect diagnostic performance of such an algorithm, but some things where patients really have a lot of images, like patients with hydrocephalus with shunts, pediatric patients with shunts who will have over the course of their lifetime many CTs, and where we have simple questions like, is there a large hematoma or is it a stroke, or does a patient have hydrocephalus? How are the ventricles over time? Is the catheter in the ventricle or where is it? For these things, it would be really useful to be able to generate a synthetic CT from biplanar, so apilateral X-ray of the skull and of the spine. And these were our very first results from our first prototype. This is about 1 year old now. On the left, you can see the spinal model that really worked quite well. It's a much easier task. On the bottom, you see the real CT, and on the top, you see the synthetic CT. That already works quite well, generating these synthetic CTs from biplanar radiographs. And on the right, you see that it's much more difficult for the skull, especially for the soft tissue, for the parenchyma. Again, this was the first version. By now, it's also not perfect, but you can start seeing large hematomas and whether ventricles are very big or very small. But we're of course working on that. It's just much more difficult to show the parenchyma because the whole parenchyma is of course encased by bone. So the things that have to be teased out by the algorithm, the differences in the Hounsfield units are very small. But we're continuing to work on that, and this is the latest version of our spinal algorithm to generate synthetic CTs from X-rays. On the left, you can see the comparison of the real CT and the synthetic CT from radiographs. And on the right, some tomographic images. So we are working on that hard and trying to get there. And then just a quick teaser, because Ender will talk about this, but I want to show the whole spectrum. Of course, trying to use machine vision in surgery, detecting anatomy. But I will leave that to Ender. And to finish my talk, just to promote our textbook for anyone who's interested in getting started themselves with research or developing their own models. Next year, we will bring out a new edition of this one. And last but not least, I want to thank everyone involved in the project that I showed today, especially Dr. Carlos Serra, who co-leads the lab together with me, and Professor Regli for his continuing support. And then, importantly, Olivier and Raffaello, who do actually most of the work that you've seen here. So many thanks for your attention, and I will be happy to answer any questions at the very end.
Thanks a lot, Victor, for very nice presentation, touching from the prediction models. And we do have a common project, which is called Fuse Machine Learning to predict outcome in fusion surgery. And going to this very nice concept of synthetic CT from plain radiographs, which allows also to reduce drastically the radiation dose to these patients, and allowing the navigation system robotics to be accurate as well. So thanks a lot. I think there will be a question at the end, and it is my pleasure to give the word to Ender. Ender, please go ahead and share your presentation.
Can you hear me? I see the presentation well.
We can hear you and we see your presentation.
Okay, thank you. Thank you very much for inviting, first of all. This is quite an honor to give this presentation to this audience. And I should warn you from the start that I'm not a neurosurgeon. So my knowledge about most of the things actually come from people like Victor and Carlo. Instead, I'm an engineer, and I try to build these algorithms to work on complicated problems that are hopefully also relevant. And today I'm going to talk about this live image-based neurosurgical guidance and roadmap generation using unsupervised embedding. And I should note that this is has been a true collaboration between ETH Zurich and Neurosurgery, University of Zurich Hospital. And it has been pushed particularly by people like Gary Sarwin and Alessandro to the state that it's in. So the question that we had in mind was endoscopic surgeries. I don't have to explain you the advantages of this, obviously, compared to open skull surgery. Patients have the surgery and then they can hopefully leave. In the same day, there's a drastic increase in the patient comfort. However, these surgeries also come with certain challenges. If you can run these videos, for instance, you see that actually interpreting these images, trying to create this mental map of where you are during the surgery requires immense expertise. These images are complicated for people like me, obviously, but I can imagine that they're quite complicated for neurosurgical residences and people who are actually starting to do these surgeries on their own. And the main difficulty is manifold, right? There is very limited field of view. You see very little amount of structure in this thing. There's very little contrast between different structures. The textures are very similar. If you know the anatomy well, and if you've done these surgeries maybe a couple of times, you know what's going on and you can recognize the things. But if you haven't, then it becomes challenging. And moreover, there's this constant change of the surgical tool being integrated. There's flushing, there's bleeding. So effectively, identification of the anatomy and orientation of oneself becomes quite challenging. Now, there has been obviously quite a number of work to address this. I'm imagining most of the advanced hospitals where this audience might be working in probably has a state-of-the-art neuronavigation tools. There is an MRI that's taken preoperatively. There's an entire set of tools that have these markers on them so they can be tracked during a surgery. You have the camera system in there that can have the stereo vision and understand exactly where those markers are, how they correspond to the preoperative MRI. So during surgery, there's a very good correspondence between the head and the preoperative MRI. Of course, this is valid until the point where the brain is open. This is valid until the point where skull is entered, and then you have pressure changes, so you have brain shift. So overall, now the preoperative MRI reflects less of the reality of what's happening during the surgery. Now, there are also multiple tools that actually support this, right? You have the intraoperative support coming from fluorescence imaging that can highlight tumoral areas, that can highlight blood vessels. You can imagine people use actually intraoperative ultrasound to give really, really cool images of the exact conditions that are being undertaken during the surgery, or you can even imagine the intraoperative MRI. Now, of course, these tools are not cost-free. You have to stop the surgery, you have to enter another set of tools, get the images, come back. If you think about the intraoperative MRI, this might take even more than just a couple of seconds. It might take even a few tens of minutes. And lastly, these are quite expensive devices. They're there in advanced operating rooms, but they're not there in everyday operating rooms. So we were discussing at the first with Carlo, then Victor, and then more people joined about this option whether actually one can now do these things without any of these. I know this sounds like a crazy idea, and to most people it still sounds I think a crazy idea, but to say, hey, we have all these advanced machine learning tools that can recognize cats and dogs and cars. Maybe they're also good enough to recognize anatomy in real-time fashion. And maybe actually, if we can do this recognition, we can also create a relative positioning on the surgical path and even perhaps predict the anatomy that will be encountered if we move in a certain direction. Effectively, basically doing the neuronavigation purely on image base. Now, at this point, what we needed was basically a data set to test these ideas. And I have to stop here to appreciate again and thank Neurosurgery at Neurosurgery, because they've effectively done a superhuman effort in curating this data set that consists of 166 videos of, in this particular pilot project, we focus on the transsphenoidal adenectomy. And they basically labeled these videos in 16 classes, so 15 anatomical structures and 1 surgical instrument class. And what you see on the right-hand side is an example of what this labeling looks like. And just to note the amount of effort that went into it. So this is a data set of roughly 3 million frames. So you had these experts going through these videos. They didn't label all the frames that would take a lifetime, but they basically labeled 19,000 frames. Like, imagine the amount of work in there. So this is crazy amount of work for sure. So what we've done was, okay, let's start from this and ask the very simple question, whether we can detect structures as we do in, for example, self-driving cars, right? As you drive, your car automatically detects the road signs, other cars. So can we do it the same thing here? Obviously, it's a bit different, right? Because now we have all these challenges of field of view, and the structures are very much alike each other. So somehow the algorithm has to put together a lot of information, a lot of context to be able to solve these things. Now, similar problems have been solved before for polyp detection and for surgical tool detection, but I should note that these problems are remain a bit on the easier end compared to this. Now, we applied the state-of-the-art object detection algorithm to this problem. And what you see on the right-hand side are these numerical results. Now, there's maybe two things to note here. One of them is, if you look at the average precision numbers for the surgical tool, I don't know if you can actually follow my mouse cursor here, but it's 94%. Effectively, the algorithms are able to detect the surgicals really well. On the other hand, for all the other structures, the accuracy drops. Right? There's a substantial difference between the instrument and the other ones. But if I compare these accuracies to what we observe in a usual object detection challenge in natural computer vision tasks, so data sets that involves various structures that we see in real life, not neurosurgical structures, then the accuracy there, which is on average 70%, kind of reflects to some extent what we have here. But maybe I spoke too much. Maybe actually what we should see is the videos. So what I show you here now, the videos, and overlaid are the detections of the algorithms. I have one video, rather easy on the top, but I shouldn't say easy, but it's quite challenging, but there's maybe clearer images. And there's another video at the bottom where there's the images are of worse quality. What is surprising here is, so the detection seems to be valid. Like, they seems to be doing a good job. Not that we don't get detection on every frame, right? There is flickering, but that's fine. That's probably fine, because what we need is some detections all around, and what we need is an algorithm to put them together. So these results were extremely motivating for us. And what we also need is that the detections do not confuse different structures with each other, because if I confuse two structures constantly, there's a consistent bias, in other words, then I won't be able to relative position myself. On the right-hand side, what we see is this confusion matrix. We see what structures are confused with what. And what we see here is in the diagonal is the correct detections, and off diagonal, non-correct detections. And it looks like I don't confuse structures with each other. I confuse structures with the background, which is probably okay, but not with each other. So I can easily say that perhaps we have this live recognition of the anatomy to an extent, because this is quite cool. Now I can actually imagine relative positioning and towards neuronavigation. Now, the only problem is, before we had these experts that actually gave us the bounding boxes, and that was quite neat, but we don't necessarily have it for relative positioning. Like, there is no expert that will tell us relatively on the surgical path, you're here or there based on the images. So instead, Gary had this quite ingenious idea to say that, hey, actually, maybe what we can do is we have these constellations of the detections, the bounding boxes. And each of these bounding boxes, they actually correspond to a different anatomical structure. And if I think about the surgical path, in a different location on this path, I should see a different constellation of bounding boxes. And by constellation, what I mean is both the presence of the bounding boxes, their relative position to each other, and their sizes. Perhaps as I move forward in the surgical path, I start seeing this red bounding box, and then it should grow as I go forward because I'm actually passing it. Another bounding box might be the case that I'm actually going through it, so it actually gets larger and larger. And then once I pass it, perhaps I see a certain constellation. And as I move forward, the constellation changes. So the idea was perhaps there is actually a way to put these constellations together and infer a relative positioning on an ideal surgical path. And this is precisely what we've done. So we built a deep learning algorithm that actually did not necessarily take the video frames, but the bounding detections at each frame. And then it put together these sequence of frames. And it basically took an n number of video frames, let's say 50 frames that came before that single time point. And using those 50 frames, it basically condensed all this information to a single number. So it has a transformer, a specific type of neural network to take all that information and using fully connected layers, go to a single number. And just to appreciate this, like basically mapping all this information to a single value. And the hope here is that single value will correspond to this virtual coordinate on the surgical path. Now here, the assumption is the particular surgery that we're working with, the transsphenoidal adenectomy, can be represented with a single path, like a one-dimensional road, if you like. Of course, more complex surgeries will require further paths, and that's the research that we're undergoing at this point with the collaborators, but a single point. Now, what we do is we basically ensure that this point can represent, or in other words, can reconstruct the entire constellation of the bounding boxes. That means that that single number should be able to tell me what bounding boxes are there in that frame and what sizes they have and what constellation they have. If it can do this, that basically means that this number actually tells me where I am, relative positioning, or this virtual coordinate. And I have basically two terms here. One, I have to basically make sure that I'm able to represent or reconstruct what boxes are there, and then the correct positioning. Now, we trained this with possibly 130 of these videos. And what I'm going to show you next is if my mouse works, if I actually now take this number, a single virtual coordinate, and basically walk through that coordinate, right? Think of it as a surgical axis, and walk through that surgical axis, and at each point reconstruct the constellation of the bounding boxes. So let me show you this video that actually shows this. So I'm actually going in that one-dimensional coordinate. And as I go forward, I see that different structures are actually getting larger and larger. The constellation is changing. However, also note that this is actually quite a smooth change, and all of a sudden certain boxes change because they basically pass those structures, and certain other boxes will start appearing. Perhaps I basically entered the skull base, now I will see different things. I actually can move forward a little bit in time to see that I have now different boxes appearing. And as I move forward, I'm actually moving forward on that surgical path. So basically, the constellation of the boxes that I should see change. Now, this was also very interesting. So what we did was we said, okay, why don't we actually make a plot? And this plot on the x-axis, on the z here, we basically plot this vertical surgical coordinate for different values, starting from 0 going to 1 in a normalized fashion. And on the x-axis, what we plot is different anatomical structures that we expect to see in the surgery. And on the plot itself, what you see is for different coordinate values, what is the probability of observing those structures? And note that when I start from 0, 0, so at the very beginning of the surgical path, I see certain structures, and these are the structures that I'm supposed to see. As I move forward, they fade away, and then I see some other structures. And this all makes sense when we think about this particular surgery. 2 different points, I'm supposed to see 2 different structures. And it looks like this virtual coordinate is able to capture this information. Now, this is basically generation again. I take those coordinate values and I generate different values, different constellations. Then what we did was we were actually interested in using this set of information, but instead we took a real video a video that was not used for training, and mapped it onto this one dimension. What we show here is, again, on the x-axis, the surgical or virtual surgical axis or coordinate. And on the y-axis, we show the real time, so the time in the surgery. And what you see here is something also interesting. So first of all, as time evolves, the surgical axis also goes higher. So that basically means I'm going deeper and deeper. So it might be the case that the higher values in the surgical axis refers to the deeper locations in the brain. Furthermore, there are certain parts in this plot where it looks like I spent a lot of time. And those are the corresponds to times, actually, if you think about the surgeries, where you're actually removing some structures. For example, around 0.6, we actually start removing the tumor itself. What is also interesting is there are certain locations where all of a sudden, the surgical axis goes to 0. And they actually correspond to the point where you retract the surgical tool and go back in. So it looks like it's doing something quite interesting. And if we look at now, again, the overall view, we had the images. From these images, we basically extracted these bounding boxes. So we recognize the anatomy in real time. From those constellations, we basically were able to map ourselves on the surgical path. So basically, for a given point, I can actually take the videos, I can detect the structures, I can map myself on the surgical path, and then I can predict what will happen if I go forward, and what am I supposed to do if I go backwards. Now, at this point, all of this, we still kind of did everything in a qualitative fashion. So next step was we tried to come up with some quantitative assessment, but note that the quantitative assessment is particularly difficult here because we don't have a ground truth value for the surgical paths. Like no one is able to give this. So instead, we did something like this. Look, if I were driving a car, and on my route, if I had 3 different landmarks, if I had the barn, if I had the factory, and if I had the hospital. If I move with the car, now I can go back and forth, so I can these structures more than once. But the first time they appear should correspond to the distance they are to the initial position of the car. So what we did was, for multiple test videos, we basically identified the depth of the depth values that we have, and the first time each structure appears in a video. If everything was perfect, this should have 100% or 1 correlation value. And what we saw was actually the correlation values are quite high. These R values are the Pearson correlation values between the first appearance type of structures and the estimated depth on this virtual surgical coordinate. So it looks like this coordinate really captures some proper depth information about being relative, but still it tells me where I am relative to other structures. And the last thing I want to show you is we did something funny and we said, okay, we can take a normal video which looks something like this. Right? So it's a normal video, there's quite a bit of flickering. Just during this normal endoscopic procedure, I go back and forth, and there's multiple structures like this. Each time I go back and forth, that basically means that I should actually map to a different value in the depth in this vertical axis, virtual coordinate. So what we can do is we can actually reorder this video such that I only go forward in depth in this virtual coordinate. And if I do this, what I see is I basically kind of cut out the parts where I go back in the image. So now there is a smoother transition between the structures. And I basically, remove the parts where I have to retract, where I have to go back a little bit and go forward. So I can reorder the entire video. And that's really everything I want to discuss. If I can pass the slides. I would like to thank, obviously, everyone who worked in this. So University of Zurich Hospital for the enormous support in this, and Lyco Microsystems for their contributions. And I should particularly thank Gary Sarwin, who actually put so much hours in this, and Alessandro, who put so much hour in this labeling to make this work possible. And I'm happy to get any questions if you have some.
Thanks a lot, Ender. Very nice presentation. Very interesting, actually, your work on creating roadmaps for surgeons and surgical procedure. And again, the Q&A session is opened. I don't see a question to you yet. I'd also want to ask to the E18 board members if they do have some comments or... Oh, there is Nicolas Sampron who left his hand. Nicolas, welcome.
Hi, Enrico. How are you?
Fine.
Can you hear me?
Fine. Yes, great.
Yeah, thank you very much. Amazing presentations, amazing presenter. Also, I would like to comment on Victor's presentation. I think it was remarkable, particularly the issue they are trying to address. And I would like to, from both, a comment on the potential scalability of this technology, since it is software technology as compared with hardware. I think that the number of patients and all around the world that can easily benefit from this technology will be different as compared with, for example, hardware technology.
Thank you, Nicholas. Yes, that's a very good point. And it applies to not only the things that I show, but also to Ender's algorithm. So the point basically is that, for example, robotics maybe is the most extreme example, but maybe even, let's say, an MRI machine or whatever technology, intraoperative ultrasound. In Europe, I guess it's not so much of a problem. We have access to all the tools. We are fools with a lot of tools. But maybe abroad, that's not the case, in rural areas. And that's where probably one of the big impacts of such technologies can be, because as you said, they are software based. So what it takes quite some, let's say, computing infrastructure to train these algorithms, usually they're not so necessarily so heavy to apply them. So you don't need a super expensive computer usually to apply most of these algorithms. And they can also be done online, right? They can also be done online. So that really would make these technologies much more accessible to everyone, especially low middle income countries, than other technologies. And so overall, the benefit might be great. So whether that is this, let's say, X-ray to CT, I mean, you could even imagine things where, for example, I mean, you know, not even every hospital in the world will have a CT scanner, but pretty much every hospital has an X-ray machine, or every general practitioner has an X-ray machine. So it would be even possible maybe in an ambulance to put an X-ray machine and see which, you know, does this patient have to go to a big center because he has a bleed, or maybe he only had a seizure, there's nothing intracranially. And the same thing with Ender. Maybe Ender, you can also talk a little bit about that, getting rid of all the tools and only basing this, as you said, on like real-time imaging.
Yeah, I can only second the opinion here. The software tools obviously have a much larger range and reach than the hardware tools. It doesn't mean that the hardware tools are not useful at all. I think the ideal scenario is you have software that can leverage existing hardware, but still able to provide something even if the hardware is not there.
Thanks a lot for your answers. And any other questions? Nikolai Gabrovsky, please.
Hello, everybody. Thank you very much for this very, very interesting presentations. I'm really impressed what you are doing and the efforts that you are putting in this. We are more or less end users, so we are seeing the product of your work. So it's impressive how difficult and how long is the way that we have to go. I just want to make a small comment. Looking at the picture of And this reminded me somehow the end of the 80s and my first computer. It was a Commodore 64. I'm not advertising this because it's not produced anymore, but I remember the enthusiasm with which we have made our first steps, making some frames and some pictures. So what I feel now that we are, in fact, with all the calculating power that we have, with all the enormous data that we have, with the completely different connections, interconnections that we have, with the completely different tools that we have, that we are just in the beginning of something that will completely change the way we work and the way we operate, the way we treat in general. So just I wanted to say thank you that you demonstrated us a little bit of your work, and it was a real pleasure, and it makes me somehow very optimistic. Thank you.
Thank you very much.
Thanks a lot, Nikolai. There are 2 questions raised from the online participants. The first one is from Davide Scorza. I try to summarize this question. It is mostly for Victor, and the synthetic CT scan, which is actually the margin of error of rebuilding imaging from a radiograph to a CT scan, or for an MRI to a CT scan, and can we rely 100% on these reconstructions, and should be regulatory issues in clinical application with regards of synthetic reconstruction, imaging reconstruction?
Yeah, it's a very good question. It's a very big question also. Generative imaging is generative, so the algorithms, these kind of algorithms make things up that they think look similar to what we want them to make. That's also actually how they are trained. So it is debatable whether we will ever use such synthetic imaging for diagnostic purposes, like really looking at, okay, describing the whole pathology of the patient after brain trauma. Does he have maybe small subarachnoid traumatic hemorrhages also? But the answer to the question really is we first have to find out. So first of all, we have to get to this level 2 that I showed, improve these algorithms so that we think, okay, now it might be interesting to start using them in maybe a clinical trial. And then we'll have to see what we can actually do with them and what is safe. So, I mean, my personal prediction will be that at some point we will quite reliably be able to distinguish between a large hemorrhage and a stroke, and maybe see if someone really has a decompensated hydrocephalus shunt failure. Simple questions like that. But I would argue that we will probably never use this, or never is a strong word, but not so soon use this for a diagnostic purpose. And what regards to regulatory affairs, that's even more difficult topic, because every medical field even is different, and every algorithm is difficult. So it's really difficult to create a legislature for these kinds of, or for machine learning in general. Yes,
absolutely right. This is also a very important field, which is the regulatory system when it comes to AI, ChatGPT, and so on. So this will be the next step. And there is a very last question before we closing from Ayman Maidan. This is for Ender and the group from Zurich. Do you also plan to do roadmaps for some other approaches like transmaxillary approaches, or in addition to transvenodal?
Yes, absolutely. So I should say that most of our problems and the questions come actually from neurosurgeons we work with, so Victor, Carlo. And the transvenodal was the simple proof of concept in a sense, because it was easily a one-dimensional road. Now we're working on extending it to more complicated approaches. So this work, I hope we will be able to provide some results very soon.
Thanks a lot. And I think we came to the end, and of course there will be a lot to discuss, and I really appreciate the work of Zurich University. We do collaborate with this group, and I think that there is a lot of promising new tools that will be developed in the field of artificial intelligence. And of course, it can be regulated. Of course, it's not foolproof, as I mentioned before, but I think we must improve our knowledge on artificial intelligence, especially from our field of simple-minded surgeons, because this will be in the next future a huge application of this computer assistance in our surgical procedures. And I think doing this kind of webinars and divulgation, it's a good way to actually make people aware about the potentials of this new tool. So again, I would like to thank Victor and Ender for the very nice and illustrative presentations on this topic, and I also thank the participants stayed with us online, and of course ENS for the support, ENS office for having put this Zoom together. And I really wish you a lovely evening, and see you soon. Thanks a lot.